Okay, what I'm going to show you now is also something that you can do yourself as homework to get a feeling of it. But I always also show the examples from that. It's up to you to do it or not, but it's quite good learning experience to try to do this homework. So suppose we want to fit an ARMA to this time series of groundwater levels. We have 24 observations a year, so 2 observations per month and 19 years worth of data. Yeah. Now, of course, this is not really a stationary time series, because what we see from this is that we see this typical seasonal behavior. Of course, there are periods where it's more drier. So you also see some multi-annual trends in there, for instance, relatively dry and relatively wet periods on time and so on. So we want to get rid of the periodicities and the trends. And that is what we're going to do. So here you see the same time series, but now it is being a yearly trend is basically decomposed into 3 components. A periodic signal that is the same every year. A trend signal that shows you the multi-annual variability of the wet and the dry periods, for instance. And then a residual, and that seems to be quite well described by, or it looks a little bit more like a stationary process. Now you can do that in R. So what is done here is in this command here, we have a data frame with a column called groundwater level, and we this data frame groundwater level is basically converted to a time series with a frequency of 24 per period, so a 24 frequency per year in this case. So this is our new Z. Z now becomes a time series, and we formulate a new variable Z decom, a decomposed Z, that uses this this command to decompose Z into 3 components, as you can see. Yeah. So the residuals, so Z ops is equal to decomposed in a seasonal trend, a seasonal variation, a trend, and residual. Yeah. And the residuals are going to be modeled with an ARMA model. Yeah, that's what we're going to do. So this, if you want to know, ZR is the residual, and we take that by that's actually the decomposed time series has 3 components. It's a data frame again, with time series 1, 2, and 3. This is time series 1, time series 2, and this is time series 3, which are the residuals. So this is plotting the residuals at a larger, plotting the residuals only, and then we can calculate the autocorrelation function of that. Yeah, we've already done that, and this is shown here. And you can see that these are significant correlations, and then they become non-significant. Yeah, and what you see is there are actually also a number of significant correlations, negative correlations, for larger lags, which is a kind of weird. So it seems that there is some periodicity in our signal that has not been properly removed. But in practice, you would say, okay, these are significant correlations, 1, 2, 3, these 3. So the correlation length would be 0.2 years, something like that. Yeah, that would be the correlation length here. Now again, this can be done in R, for instance, by the ACF command that calculates of the residual, the autocorrelation function. We make a new plot from that, a new variable, and we can plot that as well. So the next step is to fit an ARMA model to the residuals. Yeah. So this is the command to do that. We say ARMA11 fit. This is how we call the variable, the new variable that we make, or a new object. We make a new object called ARMA11 fit. And in this fit are the time series and the estimated, and also the estimated parameters is equal to ARIMA. That's a command. This is the time series that goes in, and then the order. And we say we're fitting here an ARIMA 101 model, which means because we're using 0 here, we don't do any differencing. And we don't have to do any differencing because we already removed the trends and the periodicity, and we are directly working on the residuals. Yeah. Now, if you want to do then print ARMA1 fit, you print this object, you get the coefficients, also an intercept, which usually has is close to 0, because it's after all a regression type of model, and we get an AR1 parameter of 0.501 and an MA1 parameter of minus 0.005. And these are the standard errors. Yeah. Now what you can see is that this is a significant parameter, but this one is not, because this value, if you do this value plus or minus 2 times the standard error, you get a confidence interval, and that confidence interval overlaps with the value of 0. So it's not significantly different from 0, this fitted parameter. So what you typically then do is get rid of it, and we fit a simpler model, for instance an AR1 model. So that's what we're going to do next. Before we move there, we need to expect some other things. So this sigma squared is the variance of the residuals that you have. So if we fit this ARMA11 model to our data, and we do one step ahead predictions, this is the type of this is the variance of the error that we get, of the prediction error. Yeah. This is fitted with a so-called log likelihood function. Well, this log likelihood function, the more negative it is, the smaller it is, the better. But we also have this so-called Akaikis information criterion, and we come back to that later. But this has to be as small as possible as well. Yeah. Okay, now we decide to leave out this moving average 1 parameter, and we fit a new model. Yeah. And we can see that actually, so now we fitted an AR1 model. Yeah. Now, of course, we see that the variance of the residuals is a little bit smaller. Yeah. Or a little bit larger, sorry. But we accept that because we can expect it one that seems to be doing better, but we have a non-significant parameter in it. It means that the risk of extrapolation, the risk of making an additional error for extrapolation is way too large to accept this one. Yeah? So we're going to use this. Yeah? Okay. Now, and this is then the theoretical autocorrelation that is plotted over the empirical one. And we can do that by first plotting the empirical one that we did before. And then you plot you say plot fitted ACDF. That's the object that we call it. And it's we already saw that you can get a fitted autocorrelation function by saying, okay, fitted ACF, AR is C0.051, and then the maximum lag in this case is 20 time steps. Yeah. So that's the red one here. Yeah. So this is how you do it. you basically fit a model to it. You check if all the parameters are significant. If there are certain parameters that are non-significant, you reduce the complexity of the model by throwing out that specific parameter and fit a more simple ARMA model. Once you've fitted that, you calculate also the theoretical autocorrelation function, and you compare it to the empirical one to see if it fits sufficiently. Yeah.
I have a question.
Yes, of course.
Yeah. Could you maybe explain once again why that the MA result is non-significant?
It's non-significant because if I compute a confidence interval of this one, yeah, I get minus 0.005 plus or minus 2 times this standard error. That's my interval.
Yes.
Yeah. And that interval is going to be grossly, I'm not going to calculate it here exactly, but it's going to be somewhere. So this value is between, say, minus 0.2 and plus 0.2.
Mm-hmm.
Which means that the value is not significantly different from 0.
Okay. Yeah.
So in that case, I might as well use 0 for it and not use it at all.
Okay. Yeah, thanks.
Yeah? Okay. So let's go and talk about model selection in more general, because how do we decide whether we want to use an ARMA 1.1, an ARMA 2.2, an ARMA 3.3, an ARMA 2.1, an ARMA 2.3? There are different combinations that you can use. How do you choose the best model? Now, in general, if you use more models or more model parameters, or a richer model, you would see it would fit your observed data set better, because you have more degrees of freedom to fit the model to. And the residual error variance is going to be smaller. Yeah. But of course, you're also going to have more parameters that you have to fit, and these parameters are also fitted with some degree of error. Yeah. So if you do a forecast, basically you have 2 types of errors, the same as in regression. You have a forecasting error that has 2 components. One component that is the residuals, yeah, because your model never will fit the data exactly. But you also have an error in your fitted parameters. And the more parameters you use to be fitted, the larger these parameter errors are going to be. And if you then extrapolate in time, forecast, you will see that the forecasting error increases with the number of parameters. Yeah. So you can see it like this. If we increase the number of parameters, yeah, there's 2 components to your total uncertainty. There's the residual variance that will decrease because you add more parameters, the model is going to fit your data better. But the parameter standard errors are going to be larger, because basically you're fitting more parameters on the same length of time series. So your degrees of freedom to fit each parameter decreases. Yeah. So there's a balance between the two where the total error is minimum. Yeah. So this is the number of parameters, and therefore also the complexity of the model you're going to use. So if you want to select the best model, you want to have the model that on the one hand has the smallest innovation variance, or variance of those residuals, sigma a squared, yeah. But you also want to have the smallest number of parameters, and that is called so-called Occam's razor. That's known from philosophy of science. You want to fit the model, the simplest model, to fit your problem, but not too simple. That's the idea. And there are different so-called measures or criteria that weigh optimally the number of parameters and the residual error. Yeah. And how is that done in practice? So suppose you have one single model, an ARMA PQ model, yeah, and then you basically use different orders of that model, yeah, in forecasting mode. So we fit We fit ARMA 1.1 model, we fit an ARMA 2.2 model, 2.1 model, all different combinations, yeah. And we use these models, each of these models, to do one step ahead forecasts. Then we calculate the variance of the residuals. Yeah? This is our actual observation, and this is the re-forecasted one with the fitted model. Yeah? And then you make a weighted average of, basically this is so-called Akaike's information criterion that weights the error of the model, the residual error, and the number of parameters that you use. Yeah? So if you overfit, then this one becomes larger than this one, and the information criteria increases again. Yeah. So this information criteria can be used to select the optimal model. By the way, if you apply this, at the same time you have to make sure that none of the parameters is non-significant. So what you typically do in practice is the following. You use many different candidate models, you fit them, you check if any of those models has non-significant parameters. If it is, then you throw that model out, because all the model parameters fitted need to be significant. And then with this remaining set of models, you go to see which one does best in terms of this Akaike's information criterion. So there are so-called three ways of, so this is basically how you do model identification. So what order of model do you want? Model estimation, estimate the parameters, and also verify if it's a correct model. Are the parameters significant or not in one workflow? So you define K candidate models. So this is actually even much more general. So this is a so-called, these are the parameters of a so-called SARIMA model. So it's even more general. We can also do not only include normal differencing, but also seasonal differencing to get the seasonality out in one go. But anyway, you take any set of different candidate models, use an estimation program to get all your parameters. You look to the parameter standard errors and also the parameter correlation. What is the, I'll come back to that later, but you look at the parameter standard errors. Are there any parameters that are not significantly different from zero? So those parameters, so those models with having those parameters have to be thrown out. Also, if there's a model where there are two parameters that are highly positively or negatively correlated, for instance, if you have theta 1 and theta 3, and these two are highly correlated, that means that if they're positively correlated, then a higher value of one goes together with a higher value of the other. Or if they're negatively correlated, a higher value of the one goes together with a smaller value of the other. So they are linearly dependent. And then that means that one of the parameters is redundant. So then you basically throw out a higher order parameter. Yeah. So that's a consistency check. Yeah. Then you look at the residual series from one step ahead prediction. And you fit many more candidate models, by the way. Yeah? So each of those models you fit. And you get, you only retain the models that have parameters that are significant and that doesn't show any mutual high correlations. So you get a subset of candidate models that are pass the test, in the sense that their parameters are not too highly correlated and they are significantly different from zero. And for those, you select the best model in terms of Akaike's criterion. Yeah? So that's the modern way of fitting so-called ARIMA models or seasonal ARIMA models, so-called SARIMA models, to time series data. Yeah? Okay, So let's move on to part 3, and that's looking at non-stationary processes and transfer function noise models. Yeah. So we saw that in principle, time series, especially hydrological series, are non-stationary because there are periodicities in there. There's often also seasonal or multi-annual trends in there, and you want to have a stationary random function to fit an ARMA model to. Yeah? So there's basically 3 different ways of dealing with non-stationarity. So one we already saw. That's basically you just decompose the thing into a trend, a periodic signal, a long year trend, and then a residual. And you do everything on the residuals, and then you can always add the trend and the periodicity to get the original signal back. For instance, if you're going to do forecasting or you're going to do simulation, you can always do the add these later on. Yeah, that's one way. That's the first way to do it. The second way is to fit a so-called SARIMA model to this. A SARIMA model is a seasonal ARIMA model. It means it includes you you basically difference for higher order trends, but you also get rid of yearly or multi-annual seasonality. Yeah? In one go. So you have basically so you're also fitting the order of the differencing. Yeah. And then you can directly fit actually the whole SARIMA model to this original time series. That's the second way of doing it. And these are so-called non-stationary univariate time series models. A third one is, suppose you have a other series that you observed that explains the variation of one series. So this is your target, Z, maybe groundwater level, and this may, for instance, be, I don't know, a nearby groundwater level, or a groundwater level, or this may be groundwater level, and X may be precipitation, mean potential evapotranspiration, right? So if you have more than one series, and one series is to predict it and the other series is given, then you can actually use this as an auxiliary information, as a regressor, yeah, in your time series model, to predict this one. Yeah? And this is a so-called transfer function noise model. So if I want to say how would you do, what would you do in practice if you want to apply this? Well, I'd say the following. If you don't have any explanatory variable, then I would basically do this. So explicitly get rid of the seasonal and the trend and do the ARMA modeling, so a stationary modeling on the residual. Forget about all these SARIMA models. They are way too complicated, difficult to understand, and often over-parameterized, so don't do that. But if you have auxiliary variables that explain the variation of your hydrological time series, then use transfer function noise models. They are the preferred method for non-stationary time series. Not only because they probably will perform better than first the decomposition and doing an ARMA on the residuals, but they also will be, especially in forecasting, they will probably do better. But also they have some hydrological logic behind it, right? Because after all, the groundwater level at one location is going to be resembling the one that is nearby, or the groundwater level in the next few days or in the next month is going to probably be dependent on the precipitation and the evaporation. Now, what does a general transfer function noise model look at? Well, we have a transfer model, and we have a noise model. So the transfer part is that we have a function of Zn is a function of previous values of Zn. So the groundwater level depends on the groundwater levels in the past. That's your memory. And some exogenous variable. Yeah? And this could be another groundwater level, but it could also be precipitation, for instance. Yeah? And then we add to that a noise model, and that noise model is typically assumed to be, we assume that this is an effective way of describing Zn, and that the residuals, yeah, or the residual noise is therefore stationary, and we can simply model it by an ARMA model. So this is what is done. So just give me an example of a simple linear transfer function noise model. For the transfer, also in a transfer model, we have autoregressive components, and we have so-called moving average components. But now the moving average are not noise, but are moving averages of the exogenous variable, as you can see. Yeah. So we have the moving average components Zn minus 1 to Zn minus S, and the moving average of the autoregressive components, and we have the moving average components x1 to x minus r. So we have S autoregressive parameters, and we have R moving average parameter. Yeah? And then we have a noise process. This noise process is by itself then modeled. This is called the residual noise, which is not necessarily white noise, because it can still have some correlation in it, and therefore we model it with an ARMA model. An example, Zn is delta 1 Zn minus 1. So we have one autoregressive component, and we have two moving average components, and there is the noise. Now we can again have a shorthand notation for this. Yeah? Suppose we take this transfer function model that with one autoregressive and two moving average components. We can write this. We can take the z to the one hand and all the x's to the other. So we get z minus delta 1 Zn minus 1 is omega 0 xn plus omega 1 xn minus 1. We use the backshift operator again. So this can be written as 1 minus delta 1 b times z. Yeah. And this one can be written as omega 0 plus omega 1 times b. Now we use this capital delta and this capital omega, and we can write z as a function of x like this. Yeah, and of course this can also be higher order polynomials in B and in higher order polynomials in B, both. If you have higher order, if you have more autoregressive and more moving average components. Okay. Now, for instance, if we fit this, you can play around with transfer example R. We have an X and we have an R. We have, in this case, we have this simpler model. We have two moving omega components and one delta. You can shift around with these, and you can plot X plus Z, but you can also plot the cross correlation function between the two. Yeah. So play around with that example if you want to, and then show if you shift the delta here, what happens to Z. Yeah. Now the dependency between X and Z depends on the cross correlation function. Yeah. And which, in contrast to the autocorrelation, this is not an even function in the sense that it's not symmetrical. It means that the correlation between Zn plus k and x is not the same as the correlation between Zn minus k and x, yeah? N. And that is logical, obviously, because, for instance, if x would be rainfall, and this would be the groundwater level, yeah? Obviously, it can be that the groundwater level 2 days from now, k is 2, depends on the rainfall that fell today. but it's unlikely that the rainfall of today depends on has any dependency with the groundwater level 2 days ago. Yeah. So there is a certain direction of time or causality in these type of functions, or in the autocorrelation function and in these type of transfer functions, right? Now this is an example for this particular setting of delta omega 1 and omega 2, what the cross correlation function looks like. Yeah? And you can see indeed it is not symmetrical. Yeah? Now, how do you fit a transfer function itself? So the transfer function is actually fitted by regression. It's a regression problem. So suppose we want to fit zk is equal to delta 1 k minus 1 plus omega xk plus omega 1 xk minus 1. Yeah. We can basically make a vector of z's that depend on, so in this case z2 is equal to z1 times delta 1 plus omega 0 plus x1 plus omega 1 times x1. Yeah. Z3 is delta 1 times Z2 plus omega 0 times x3 plus omega 1 times x2, etc. So we have this matrix vector system, which can be, so if we call this matrix M, yeah, we can invert this thing. We can minimize actually the variance of the residuals by this particular thing here. Yeah? By the way, in reality, this is ordinary linear regression. In reality, because the residuals, which is this series N here, these residuals are not uncorrelated in time, because we fit an ARMA model to it. It may well, instead of ordinary least squares, we have to use so-called generalized least squares, where you have to provide the variance covariance. You have to provide basically the covariances between. You have to provide the correlation between the residuals, basically. So you fit it together with an ARMA model. But in reality, this is fitted, yeah. You get the so-called, you fit this, you get the parameters of your transfer function. Then you apply this to your observations, you get your residuals, and we fit an ARMA model to the residuals. Yeah. So an AR1 model, an ARMA 1.1 model, or an ARMA 1.2 model, etc. Yeah. Now, it can also be that you have multiple inputs. For instance, suppose groundwater levels are determined not only by precipitation and evaporation, but also determined by groundwater pumping nearby, or there may be a river level or a level of the polder network of ditches that may be changed over time. Yeah. So what you typically then do is decompose the total time series into different transfer components and an ARMA model to simulate the residuals. This could, for instance, be precipitation minus evaporation. This could be, for instance, pumping rate of a nearby pumping station. And this could be, for instance, the nearby river levels. Yeah. And this decomposition is of great value. For instance, we have a hydraulic head series here, and we see the variation of it. Now, this is the part after fitting the transfer function, we fitted two different transfer functions. One that where x is equal to precipitation minus the potential evapotranspiration, and the other one is fitted with a nearby extraction. And then you can see actually the effect of both. Yeah. And why is that? And then, of course, this is the unexplained part. And why is that interesting? Now, here you see that actually there is a average effect of the pumping of minus 0.5. Yeah? It means that you can actually and if this effect, if the parameters of this particular transfer function model, if they are significant, you can actually also for a court of laws show that there is a significant effect, and also the size of that effect can be calculated, of the groundwater pumping on the groundwater levels. So if a farmer, for instance, has damage, desiccation damage, because of a nearby pumping station, then this type of time series analysis, transfer function noise modeling, is used to determine what the effect is of the pumping on the groundwater levels, and if this effect is significant, and if significant, what the size is of this effect, and this effect can then be translated, if you know the relation between groundwater level and crop production, for instance, can be related to a decrease in crop productivity, and therefore what amount of money a drinking water company needs to pay the farmer on a yearly basis to correct for to compensate for crop losses. Yeah? So this is how this type of time series analysis in the Netherlands has been used a lot. And a well-known program that you can look up that people have been using is Meniantis. Meniantis is based on MATLAB, but there are also Python type of models that are used these days. You can also look at Python for more automatic time series analysis modeling that allow you to very quickly choose a groundwater level series and then decompose it into different explanatory variables, precipitation, evaporation, nearby pumping abstractions, and so on, to do such an analysis.